Welcome to Hence the Future podcast. I'm Justin Clark,
I'm Mattimore Cronin.
and today we're discussing the future of quantum computing. So, Mattimore, maybe you talk a little bit about why we're even talking about quantum computing right now?
Yeah, a lot of people think of quantum physics as a subset of physics as a whole. So they think of quantum physics as just dealing with the small things and it's a relatively niche area. And that conception is so wrong because really what quantum physics is it's the most up-to-date, most accurate model that we have for the entire universe, right? So it's more accurate at predicting what goes on in the universe than Newtonian physics for sure, and even then relativity. And I just want to open with a quote that I really like from Seth Lloyd, who's one of the fathers of quantum computing. And he says that the universe is governed by the laws of quantum mechanics. The history of the universe is, in effect, a huge and ongoing quantum computation. The universe is a quantum computer. And
That's interesting. Yeah, I
yeah,
like that.
I mean, that quote really sums up why quantum computing is just one of the most important topics we've discussed on this podcast because it has applications for many of the other topics we've discussed previously. So,
Hmm.
how fast we progress with nuclear, how fast we progress with AI, how fast we
Hmm.
progress with chemistry or biology. A lot of these can be growth hacked using quantum techniques. And
Yeah. It,
theoretically.
yeah, and just to kind of expand on what you were saying about quantum physics being a better description of nature, and really it's describing the fundamental building blocks of nature. The
Hmm.
reason that we still have or that we're using stuff like relativity and just kind of ignoring quantum physics at the bigger level is because those other models are really good at predicting really big
Right.
objects. So like
Macro
the
phenomenon.
the quantum fluctuations and stuff aren't really apparent in really large objects. So that's why we still use
Yeah,
stuff
but
like that.
they are a prerequisite for large objects. Like for instance, your cell phone or your computer is dependent on our understanding of
Oh yeah.
silicon, and
Yeah.
without our understanding of quantum mechanics, we wouldn't understand silicon. We wouldn't be able to
Mhm.
create smartphones or computers. So we can thank our Instagram accounts to quantum scientists.
Yeah, for
and
real.
and then another, to go even beyond that, nuclear fusion is what happens in the sun. We talked about that on the future
Hmm.
of nuclear. And that also is dependent on quantum tunneling, which is a phenomenon within quantum mechanics. Because basically, what happens is two hydrogen atoms bounce into each other, and then the protons within their nuclei quantum tunnel into each other to combine to release all of this energy and become one. And without the ability to quantum tunnel, which is literally going through a wall that you would think is like a physical barrier, there would
Uh-huh.
be no energy in the sun, there would be no heat or sunlight, there would be no life on Earth. We wouldn't be here. So we can thank our entire life and our technological prowess
Yeah.
to our understanding of quantum mechanics and quantum computation.
Yeah. Yeah, and it's really interesting too that quantum computing was conceived a long time ago. Like Richard Feynman was one of the early people
Hmm.
that kind of said, "Oh, if we can compute stuff, which is basically just transforming some input information to some output information, what if we just change the way that the information itself is stored in the first place and the type of information it is? And maybe that would change the types of computations we can do."
Right. And I would love to hear how you think of a quantum computer as being distinct from a classical computer. Because I
Mm,
know, like, classical computers, they're all bits, they're ones and zeros, and it's got to be either one or the other. Whereas with
mhm,
quantum computer, there's this really difficult to grasp concept of superposition, where something
mhm.
can be some combination of one and zero, where it's like 90% one, 10% zero, 99%.
Yeah.
Like it just can fluctuate between any proportion of one and zero. And
Yeah.
obviously that allows for much more computation, but maybe you can explain it more clearly.
Yeah, so the state of a qubit, or the state of superposition, really is sort of a transient state. And then, like, I'm sure most people have heard of when you observe or when you measure
Hmm.
a quantum state, it collapses something called a wave function. So this wave function is basically telling us what the probability of this, where this particle is or something else. And with quantum computing, like I was saying before, we're really just changing the substrate, or the way that the information itself is encoded. Because with classical computing, information, like you said, is stored in bits, zeros or ones. And
Hmm.
in the physical world, the way those are actually represented in the physical world on computers are typically through voltages. So a zero would be like no voltage or a very low voltage,
Right, it's
and
like
then
a
a
light
one,
switch.
yeah, pretty much. And you can, when you combine all of these circuits, you can, I'm sure people have seen videos of people like creating circuits of lights.
Hmm.
You take one switch, and or even played with lights, two light switches in the same room that target the same light. You can play with them. If you turn one on and then the other on, it just turns the light off. It's really kind of the same
Right.
thing with
Like,
a bit.
yeah, like I've heard one metaphor that even the most powerful computers we have today, classical computers, it's basically just like having an army of, fourth graders doing
Yeah.
very simple math for you. And that's
Hmm.
basically how classical computation works. You have these very simple functions like and, or, plus, multiply,
Yep.
and then you're doing these computations. And that's great if you have a pretty straightforward problem. But if you have an optimization problem, that requires like factoring prime numbers or something that just has many different potential outcomes, then
Hmm.
you're much better off with a quantum computer that is based on probabilities and can sort of operate in parallel.
Yeah, and to kind of expand on that a little bit further, like you said, there are these operations with classical computers, like
Hmm.
and, or. So if you're doing and, it's like if I have two bits that are one and one, then that is the output is one. And there's all these rules for gates, and the output can only be a zero or a one.
Hmm.
And the weird thing is, so there are still gates in quantum computing, but those gates are way more flexible. So you can do like the square root of and, or something crazy like that. And then really what these gates are is just a matrix operation. So
Yeah.
you can define quantum algorithms basically through linear algebra,
Huh.
through matrix operations, which I think is pretty cool. But that leads to some other issues that we'll get to maybe later. But really, quantum computing is like, how do we, instead of voltages, how do we encode information in a system that has quantum properties? So the really what we care about is something called a qubit,
Hmm.
which is a zero or a one, or zero and a one at the same time with some probability of each. But if you remember in like high school algebra when we looked at complex numbers with a real part and an imaginary part,
Hmm.
it's actually sort of similar with a qubit. When you try to express a qubit mathematically, it's like it has a zero part and it also has a one part.
Hmm.
And that's kind of, it lends itself really nicely to linear algebra, so you can create all of these mathematical operations on a complex number or a qubit theoretically. And that's this math actually makes it easier to develop conceptually what sort of quantum algorithms we
Yeah.
can write.
And that's one of the defining features of quantum computing is that it's something that's relatively straightforward to express mathematically, but it's really difficult to actually grasp. I mean, there have been some famous quotes, for instance, from people like Richard Feynman when talking about what quantum computing is, and he said, I think I can safely say that nobody understands quantum mechanics. Or
Yeah.
another quote is, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And then the most famous one's probably Einstein's, like, God does not play dice, meaning like God does not have probabilistic outcomes. There is a very definitive outcome. And
Uh,
that's what's so difficult to grasp about quantum physics in general is the idea of uncertainty. And towards the end of this episode, before we get into the future scenarios, I want to talk about some of the bigger questions, like what does this mean as far as, many worlds theory versus just a singular reality that we know once the function basically does the wave function collapse into one reality as it seems to, or are there really multiple realities being generated from quantum computing?
mhm.
And then, free will is also an open question, like how much is truly random versus something that we're driving on on some level, like we're flipping quarks and the spin of different, positions versus it just
Mhm.
happening. And then
Yeah.
consciousness is the other thing, but maybe it's a little
Yeah.
early to talk about those now, but like when you try to model your thoughts around the workings of quantum mechanics, it just shifts your perception, your perspective of how everything could function. And I think that's what's so exciting about this space is that
Mhm.
if we can like upgrade our understanding to think of the world as in the way that nature computes, because the nature computes as a quantum computer, then that opens up our understanding to just a whole another level.
Mhm. Yeah, and I think maybe I'll just round out what what a quantum computation actually is, and then we can, start
Yeah.
expanding this conversation a
And
little
you
bit.
should say a little bit about Moore's law too. I think that's a good way for people
Yeah,
to.
yeah. So one of the main motivations of quantum computing is that this thing called Moore's law is potentially coming to an end at some point in the next couple decades, potentially. But really, Moore's law states, and this is the law that says that transistors on a in computers, the number of transistors on a circuit board can basically double every 2 years, or I think at some
And the
point it
price
turned
will
into
be cut
18
in
months.
half.
Yeah, 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 yeah.
Basically, it's the law that governs why iPhones keep getting better and better, and
Yeah,
the
it's a
older
good
ones get
proxy.
cheaper and cheaper. Yeah.
Yeah, it's a good proxy for the computational power of any computer, really, of any classical computer.
And it drives the
But,
tech sector to a large extent, the profits.
mhm. And one of the things, though, about this is you can only decrease the size of transistors so much before they're so small that a little bit of extra heat can cause these voltages to go way out of whack, and then there's a bunch of error involved in these computers, in these circuit boards. And the problem with that is, we can only make transistors so small,
Right.
which means the end of Moore's law, at least in the era of classical computing, is done. So there have been attempts to try alternate computing methods, and obviously quantum computing is one of those. There is also molecular computing. So, for example, like we said, computing is really just processing information, taking some information and then outputting information. Our DNA is another form of information, and there have been people that are trying to work with molecular computing or DNA computing, where basically the substrate of computation is RNA and DNA. So that's a potentially interesting avenue, um, but I think it's a little bit more niche than quantum computing.
Yeah, I
Um,
mean, the way I think about it is that when we go small enough, and remember, transistors are already like, I forget what it was, but like 1/100th the size of a red blood cell. Like they're really small. And when we go much lower, which is probably going to happen in, like you said, in the next couple of decades, like the next 10, 12, 15 years, is it's going to get so small that when you have one of these gates, one of these logic gates, like an AND or an OR gate, it will literally just quantum tunnel through the gate and go to the other side. So
yeah.
obviously that would totally screw up your classical computation. But if instead you could have a computer that leveraged that ability to quantum tunnel, then
Mhm.
that would be obviously a great outcome because I mean, I always come back to the double slit experiment when I'm trying to visualize it, which is basically like you have two slits and you're shooting some sort of atom or electron through one of those slits, and before you measure, it appears as a probabilistic wave function where it could go through either slit, pretty much 50-50 chance. But whenever you measure, it definitely goes through one of the gates. And
Mm-hmm.
if you do it with multiple entangled electrons, then if you know what one of the outcomes is, you will know for certain what the other outcome is. So it sort of allows for like many parallel computations, and then once you measure, you kind of know what all of them are if they've been
Yeah.
entangled. But I want to ask you about like what are some of the real difficulties in making this feasible with like an actual physical quantum computer? And I know like, for instance, the temperature has a bit, like one of the biggest challenges is that it needs to be absolute
Mm-hmm.
zero. So maybe you could say a little bit about why it needs to be near absolute zero and what some of the other logistical difficulties are.
Yeah, I mean, I would like to expand a little bit on what you said about the double slit experiment, because
Sure.
really, a quantum computation is not all that different. Really, we're trying to have some particle that behaves in a quantum fashion, or a bunch of particles, and we'll call these qubits from now on.
Hmm.
Um, Really you need to put them in some starting state, which is a really high energy state, and then it'll evolve through this process. It'll go through quantum gates in this probabilistic fashion, and it'll evolve to the lowest energy state possible. And whatever this low energy state is, it's still a probability distribution, but you kind of have a good idea of what the outcome should be, especially when you measure the outcome. So it's really just kind of an evolution of qubits or particles in these starting states, and then it goes to
Hmm.
it evolves naturally to some lower state. And that's exactly how nature works. That's exactly what everything is doing. It's trying to go to a lower energy state. Um, so yeah, there are,
And why does it need to be near absolute zero for this to work where you can actually measure it?
yeah,
And
so
and what's and then also like what how is there a limit to how long they cohere? And I know that's like one
yeah,
of the
yeah, that's like the big issue in quantum computing right now. So the problem with quantum computing is we're trying to control the quantumness of
hmm.
everything. So we manually the computers will manually entangle and put everything in superposition, which is a feat in and of itself for the most part. But the real challenge is keeping the all of the different qubits. Let's say we have 20 qubits. We have to keep them all cohered, which basically means the qubits are speaking the same language, like they can communicate with each other, which is totally necessary for a computation to make any sense and to be useful. And it turns out that keeping these states in a coherent fashion or in a coherent state is really, really hard. And like you said, one of the reasons it's hard is because there's so much interference from the outside world.
Hmm.
So heat is one of those things that can interfere with the coherence, or it can decohere
Right.
qubits. So we try to keep the quantum computers so cold that it's measured in microkelvin.
Right.
It's so close to absolute zero, which is the coldest it can possibly get.
Right. It's
Um,
0.015 Kelvin, which is colder than outer space.
and that's just some, I mean, some are even colder than that, like as cold
Wow.
as possible,
But
basically.
I find it interesting also that you can never truly achieve absolute zero because of the Heisenberg uncertainty principle. Like an electron will just appear out of nowhere, even if it's absolute zero, which means no energy, no heat, basically
So
no.
energy just kind of
It will
comes into
literally
the
just
state
pop
like
into existence because of the Heisenberg uncertainty principle. So we can never get totally to absolute zero. And I mean, so much about this is just fascinating to me. And like the idea of entanglement is so fascinating to me because literally what happens in these quantum computers is you just bump some electrons into each other or some nuclei into each other, and then they become entangled. And when you think about like how this could manifest itself in the macro world, it's like if you meet, if you meet like a girl at a bar and you have like an instant connection with her and you're like both thinking about each other afterwards, like, oh man, should I text her? Like, is she thinking about me? And if you truly are both thinking about each other, it's like your electrons in your nuclei are orbiting all the way in her brain, and her electrons in her nuclei are orbiting all the way out in your brain, and you're like in some sense entangled. And you know, it's funny. Like, I mean, my mom is very religious, and growing up, she would say to me like, "Oh, you should only ever have sex with someone who you're in love with, because if you have sex with someone, your souls are intertwined." And I always thought that was kind of ridiculous. But when you think about quantum entanglement, there probably is some truth to that. Like the more
Yeah.
intimately involved you are with another being, especially another conscious being, because consciousness seems to operate on some quantum level, you do become entangled. And entanglement seems to also be an argument for all of the cosmos being interconnected and us all in some being the universe rather than like some external being having created it, unless you believe in the simulation hypothesis, which also seems to fit quantum physics quite nicely.
Mhm.
So, I mean, there's just so many ways that you can interpret the macroscopic world differently once you understand how the subatomic world is operating on a quantum level.
Yeah, and that's one of the cool things with, and I don't know, how I feel about
No, I know. It's
us
all
being
very.
entangled, with some, because obviously there's a lot more to entangling particles than just bumping into each other. Like there's more things that we don't understand than things we do understand about quantum physics.
Right.
It's really good, there are some really good measurements, but I think, or really good predictions that quantum computing has, but it's still,
It's so
we still
early.
have such a limited understanding of it. Um, but yeah, I mean, there's so many cool things just by trying to get quantum computing. We're getting better at physics. We're getting better at
Right.
understanding how to manipulate our environment. So that's something that's really interesting to me. And maybe, maybe we talk about that. Or you asked me a question earlier, and then I wanted to finish up the
Yeah,
talk
that's
of
all
what a
right.
quantum computation was.
Yeah, I
Um,
mean, I think at this stage it would be good to get a sense for what are some of the different players in quantum computing, what are some of their
mhm.
approaches, and then after we sort of get a lay of the land there, then we can talk about some of the use cases and applications. And you talked about how we are reaching the end of Moore's law, and so understandably, there's some major investment going on in quantum computers. It's still very early. I mean, when we looked through our data, basically the projections are all just projections, right? There's only been a few years of actual investment in quantum computing, actual patents, because
Mhm.
quantum computers have only been feasible in the very recent past. So, but the interesting thing that I'm seeing is that there are some new players that I had never heard about. So, you've got IBM, Microsoft, and Google, but then you have new players like D-Wave and Rigetti. And
Mhm.
I'm curious how you see the lay of the land and what the different, approaches are that these players are taking.
Mhm. Yeah, so with quantum computing, there's no one best way to design a qubit. And really that's what everyone's trying to do is how can we design qubits so that the amount of errors that
Hmm.
happen, and there's a bunch of different sources of errors. And I think that's actually one of the other things that
The error
I didn't
rate.
talk about.
Yeah.
Yeah, the error rate, and that's something that's caused by, the heat. So that's why we need almost absolute zero in our quantum computations. We also need it to be these computers to be in a vacuum or a near
Hmm.
vacuum, because just regular atmospheric molecules like
Right.
CO2 and
Or
oxygen,
like if you're near
um,
granite and radiation is coming out, or
yeah, like
like.
there's so many there's so many different things that can affect and decohere these qubits. And what everyone is trying to do is design a qubit that is as stable as possible and has the lowest error rate, because there's this talk of once we achieve a 50 qubit quantum computer, that's called quantum supremacy, which basically means beyond 50 qubits, a quantum computer can outperform the top performing supercomputer in the world today. But that's there's a little bit of a
Well,
that's not
well, because
exactly
I
true
mean, I'm looking
because
at a chart right now from CB Insights that shows that Google achieved 72 qubits in 2018, and Rigetti achieved 128 qubits in 2019. But
or
the
they said that they'll release 128 qubits in 2019. It's
oh,
not
okay,
official yet. Yeah.
okay. But it sounds like we are near that level that like what you're referring to as like sort of like a tipping point. However, I don't know what their error rate is because there's that chart that basically shows that in order to have a meaningful improvement in computational power, you need both an increase in the number of qubits and you need a decrease in the error rate. If you just increase
Yeah.
the qubits and the error rate continues, then you're not going to actually have more computational power. And you could
Yeah.
kind of think of it as like, if you have this qubit and if you're emitting some microwaves to flip it into a certain position, but you
Mhm.
don't quite get the frequency right. There's a little bit of interference, and maybe 99% of the time it flips in the way that you're predicting, but 1% of the time it just doesn't change, which would be in line with quantum uncertainty principle.
Mhm.
Then that's a 1% error rate. And 1% is pretty bad compared to classical computers. So to get this to a level where it's like competitive with classical computers as far as an error rate is really, really hard. And
Yeah.
some people, even that I've researched, have thought that we may never achieve an error rate that rivals classical computers. But that doesn't mean it
Yeah.
won't still be useful for other, optimization problems
Y- Yeah, and it's expected that the error rates will be higher with with quantum computing, because I mean just the sheer fact that the output is a continuous number, just a minor error of, a thousandth of if you have if you read out a like point 999991 and then 0.0001 for zero, like there's it's not exactly 0 and 1, even though the probability is
hmm
almost exactly this zero, or points to it being one. So there's just the fact that qubits are continuous numbers rather than a discrete 0 or 1.
hmm
That adds a lot of error. But there's been work. Peter Shor is one of the fathers of quantum computing, and he's come up with several different things. But one of the things he came up with is quantum error correction,
hmm.
which uses qubits to correct other qubits. But you need a lot of qubits to fully correct a single qubit. So
Interesting. Is it
when
like
you
getting a
see
larger
these,
sample size, kind of like in
um,
statistics?
no, it's really just adding redundancy
Mm.
to each qubit. Because I mean the same thing happens in classical computers, because information is lost, especially when you send information over a network. You're
hmm
not guaranteed to have all the information present, but you have these things called checksums, which is kind of like this thing that'll you can send in a code, and then you can kind of like cross-reference this code with what you got and see if there's any errors, and if there was an error, for sure if
hmm
there was one. So there's a lot of things in classical computing, and there have been several decades of work on error correction. um, so we're still kind of in the early stages of quantum error correction, and Peter Shor has he proposed some ideas for how to do this, and they seem to be good, and that's what I think a lot of these companies are doing when they're creating actual quantum computers and designing these qubits that have the lowest error rate as possible. But obviously, we don't want to for every one qubit, we don't want another 10 qubits to correct the error of that qubit.
hmm
That starts to really make it hard to have a quantum computer that, can do anything useful, which we don't
Yeah.
really right now.
So, who of the major players would you put your money on as being in the best position to have the lowest error rate, highest number of qubits, basically just the best quantum computer out there? I mean, I know it's so
Yeah,
early, but
the one that I find really interesting is Microsoft. So they're
hmm
trying to design something called a topological quantum computer. And they're using, so this is, I believe, still completely theoretical. And their qubits are created with these things called quasi-particles.
hmm.
Um, and I don't, the last time I looked into this, they didn't even know if this quasi-particle existed. Um,
Well,
so
I've heard
they're,
of qubits as just being defined as virtual atoms. So you think that's
well,
like,
there's a lot of different ways.
hmm,
Well, so that's a little different. A
okay.
virtual, um, I think, yeah, I'm not sure
I'm
what the
just I'm just
details.
wondering how much is terminology versus like a fundamentally different type of
So this is
particle.
a fundamentally different type of
Huh.
quantum computer. It's basically using these quasi-particles that can be put into this structure. It's a topological structure called a braid. And the reason this braid is important is because the braid itself is more robust to interference.
Hmm.
So this is potentially the most stable qubit that could be created. And I think they're doing something that's so new and so different that it's almost purely research and almost purely theoretical at this point. I don't even know if they have like a
That's
working
really interesting. It
computer.
almost makes me think of like if you've ever seen a visualization of string theory where it's kind of like those tubes that kind of go like, you know, pervade through different dimensions. Like
Hmm.
that's almost like a similar kind of structure to what you're talking about. I wonder if that has any relation to why it's better able to withstand interference.
Yeah, it's just, yeah, I'm not really sure. Like, there's a lot of really deep theoretical particle physics going on.
Right,
But
right.
but what they say is that this structure is just more stable and can remain coherent for a lot longer
Hmm.
than all of these others because it can actually interact with higher temperatures and with oxygen and CO2 and all of these different things that cause these basic qubits to become decohered.
Hmm.
Um, so it's one of those that I think is like if they can pull that off, I think Microsoft is going to
Yeah.
win out in that one. I don't know if there's any like top secret theoretical stuff going on at Google, IBM, Intel, like
Right.
all of these companies might be doing something similar, but I think long term, to answer your question, if this um, this qubit, this topological qubit can exist, then I think that one is probably going to be the most stable and probably the most likely to see the general public's
Right.
device in the general public's devices.
Yeah, and from a patent perspective, Microsoft is the third has the third most quantum computing patents after
Mm.
IBM is second and then D-Wave is number one.
Oh
But
yeah.
it's
So I want to talk about D-Wave for a second too, because there's a lot
okay,
of
sure.
misconceptions about that. So D-Wave, so they came out with a over 2,000 qubit system, and I'm
Wow.
I'm quote I'm quoting for people that are only listening. Um, the reason I put it in quotes is because they aren't designing a universal quantum computer. Really, what they have is something that's more like a quantum annealer, which is designed to solve very specific problems. And the other thing is, I think a lot of it could be either a marketing push or something else, but there's a lot of controversy around D-Wave sometimes because they claim to have a 2000 qubit computer when they have extremely high error rates and they
Hmm.
also can't do a lot of the main quantum algorithms because it's not a universal quantum computer. So they couldn't do anything like prime factorization and some of these other
So what
more like
is the more narrow problem that they are trying to solve?
so that and I'm so there's a lot of potential promise with them in optimization problems. So
Mm,
they put a paper, let me figure out what the exact number is. Yeah, so with annealing problems, which is if you think so to kind of describe what annealing is, it's an optimization problem. So if you think of this flat surface or like a sphere, I guess, so like the Earth with a bunch of peaks and valleys,
hmm
the only information you have is where you are right now, like what your elevation is, and you want to find the lowest possible elevation. The In the classical case, you have to search every single possible place if you want to find the optimal solution, and
hmm
that can take an unreasonable amount of time. So really what people have to do now is sort of approximate what the best solution might be. And there's similar optimization problems in machine learning, for example. But really, what this quantum annealing can do that D-Wave's computers are potentially good at is basically just go to the globally minimum valley immediately. So it's almost like it cuts right through all the hills and it goes directly to the global minimum, which
hmm
is really good for certain optimization problems, especially if you think of this hilly surface in hundreds or thousands of dimensions,
Hmm.
which, by default we can't think of that because
Right.
it's completely impossible to visualize. But it makes the optimization problems really hard to solve. Um, but with this quantum annealing, this paper said that they can solve these problems or some instances of these problems 100 million times faster than their classical counterparts. So
But like, what's an actual So like what you wanted to know the lowest depth. What would that be useful for?
okay, so that's just a way of visualizing this space. Really,
hmm
when you're thinking of an optimization problem, you think of this giant space as a loss function or an objective function. The objective function mathematically has some sort of geometrical shape, whether or
Hmm.
not it's possible to visualize that. So any machine learning problem, um, we're trying to find a minimum of a
Right. Right.
objective function. And if you were to somehow visualize this objective function space, it would look like peaks and valleys, but these peaks and valleys might be in hundreds or thousands or millions of dimensions.
Right.
So it's the this peaks and valleys
You could think of it
analogy.
kind of like
Yeah,
if you were maximizing for your own happiness in life, there may be multiple equal peaks on that
yeah,
happiness landscape where
yeah,
maybe you'd be super happy being a stay-at-home dad who writes crime novels, and
yeah,
likewise you'd be really happy as a travel photographer, as a single person just living up your
mhm,
life. And those are very different, but you may have equal levels of happiness. So you
yeah,
could imagine that like classical is kind of like, just trying to just brute computing power to like try all the various
mhm,
possibilities. Whereas with quantum, it's more like you're like sending out little sentinels in all directions, and then boom, you measure them all at once, and you find like which one has achieved the
yeah,
highest peak. Um,
yeah.
so
And
that's
that, I
it,
mean, that's essentially what it boils down to, these
right?
optimizations.
So I'd like to now get into if we really had a a optimistic outcome with what these computers can do, what use cases would open up to us? What would we be able to do with a highly functioning quantum computer that we cannot do today?
Yeah,
And
so I think the first obvious one that we hear about all the time is quantum cryptography.
hmm
So what we hear about is that quantum computing can break all of the current technology. It can break all of the current encryption methods because we use a version of like prime factorization or the um, like
right,
if you could prime factor these keys that are
like
used
you have
to
a private
secure
key
the
and a
information.
public key, and by just having the public key, you could find the prime number to get the private key, but with traditional computers, it would just take like
It would
hundreds of
take
years or thousands of years.
yeah,
Whereas,
more than the time of the universe, like the length of the universe. So
right.
it's not going to happen with classical computers.
But with a quantum computer, it could potentially happen in minutes.
Yeah, and that's through something called Shor's algorithm. So again, Peter Shor came up with this algorithm where um,
Oh, for
it
sure.
can factor, yeah, SHOR.
Yeah.
It can factor these
I'm,
giant prime numbers
I
and
mean, I've heard
essentially
one person, I was watching this TED talk of someone saying that it's possible that in the future we could have a quantum internet that is completely secure, where you could communicate with people, you could send money, you could transact without any risk whatsoever of someone breaking that encryption. Because to break the encryption, you'd have to break the laws of quantum mechanics themselves. And
yeah.
that's pretty awesome.
And the reason for that is if you design your key and it's in this like weird transient state, you know for sure when something that was quantum has been observed
Right.
because the wave function collapses. So
Right.
you can tell if somebody tries to read the information that's being sent,
It's like tripping an
then
alarm, like
yeah,
someone breaking into
exactly.
your house.
The wave function of your information, of your quantum information that's being sent over this network collapses. So you know exactly what happens. And also, it's not necessarily useful to even read
Right.
information because once it collapses, it just kind of falls into whatever state it was in. So it's like you said, completely secure. You'd have to literally break the laws of physics as we know them today. Now, there might be some additions to the laws of physics in the next couple hundred years that are like, okay, well, maybe there's this loophole in physics that
Right.
we can break it. But for the foreseeable
Yeah.
future, no, like
For the people
that's not
running
going
the
to happen.
simulation, they can exploit the loopholes, but for the people in the simulation, no one's breaking in.
Yeah, pretty much. Yeah, and to kind of talk about simulation, like expand on that a
Well,
little
I
bit.
want to talk about the use case. We should round out the use cases
Well, that's
first.
what I mean. I was
Oh,
talking about
okay. Sure. Yeah, go ahead.
so we can simulate the physical world. We can simulate chemical interactions. We can simulate actual
Right.
physical
Well, I want to
scenarios.
linger on chemical interactions because that's something that when I was researching this, I was shocked at how bad we are at simulating chemical systems. So I found that, um, I'm just looking here at this diagram, and it shows that the largest chemical structure that we can simulate is this, like, what is it, manganese,
Hmm.
but it's just some random enzyme, and like literally the all of our computing power put together can just simulate this one little enzyme, and
By itself,
by
right? Like in a
itself.
silo.
Yeah,
Yeah.
just like what this enzyme does. And so
Uh,
if you're trying to make breakthroughs in medicine and find, how does a cancer cell move, what makes it progress, how can we cure cancer, how can we create cures for people based on their specific genome. I've read that through quantum computing, we could potentially encode every person's genome, all 8 billion people, and potentially then you could just have that data on file, and then if you get some disease, they could just you could run through a quantum computer like many different possibilities of ways to treat that disease based on your genome, and then come out with the right one. But just the
yeah.
ability to model different chemical structures, enzymes,
Yeah.
proteins, molecules, cancer cells,
Medicines.
medicines. Yeah.
Yeah.
Like that ability, we're so limited right now, and the doors of what's possible will just open up tremendously if we are
Mhm.
able to create some working quantum computers at scale.
Yeah, and one of the other things that's really interesting is what if we can simulate a couple neurons? Like there's a bunch of different atoms in the cell, but what if we can start to model even more neurons and more
That
neurons
could
and
be
more
the first
neurons?
creation of artificial consciousness.
Yeah. because if consciousness does rely on quantum effects, we're never going to get there with classical
Right,
computing,
right.
because classical computing, and I heard this recently on the Joe Rogan and Naval
Yeah.
podcast,
Hmm.
um, where basically Naval was saying he thinks artificial general intelligence is not something to worry about because classical computers can't model. Sure, they can model the sort of output behavior of a neuron, like all of these different neurons kind of work together and then fire in this pattern. But what we can't do is model the actual structure of the neuron, like the atomic
Hmm.
structure of the neuron. But if we can actually do this with quantum computers, we might get to a point where we're truly simulating a mind, and we're
Right,
truly simulating a sentient mind.
right.
It might be one of the prerequisites for artificial general intelligence, or at
Hmm.
least sentient AGI. So there's a lot of really interesting things that could come from this, and then it's really
Yeah.
mind blowing to think about all of the different things. We might even come up with a theory of everything that can more tightly integrate quantum physics and gravity. So
Right.
there's so many different things that we can do here, that I think
There's
in the
also the
next.
search for extraterrestrial life, for habitable planets, for knowing when and what path like asteroids could come at us, and
Oh
um,
yeah,
yeah. So there's oh, by the way, it was nitrogen or nitrogenase was the enzyme, by the way.
nitrogens. Okay.
Understanding climate change, but yeah, the most exciting ones to me are really the medical applications and the AI, or brain machine interface applications. Like,
Hmm.
another interesting element of a quantum internet could be that you could basically transport your mind to another place at faster than the speed of light through entanglement. So you could imagine, like, if you're on a Zoom call or like a Skype call with someone who's like on Mars, and there's no delay, like you're instantaneously conversing with this person. That would be
Hmm.
one, like, maybe medium term application. And then in the far future, you could imagine like sending out probes to every corner of the cosmos, and then you could just have like a control center where you basically just like VR into this, like each of those probes, and you can sort of like it kind of reminds me of this quote that Elon Musk had where he said, "Why would you want to teleport your body? Just teleport your consciousness." Like
The interesting thing there, like I'm very curious to see how this works, but I know there are issues with copying quantum information. Like
huh.
you can't copy exactly a quantum system and put it somewhere else. And that's where there's like this misconception about like spooky action at a distance, because it's not actually not always a useful property, because when you read one so if two electrons are entangled and you measure one of those, they become disentangled, and there's not.
uh,
So there's different things that make these sorts of things difficult. But I think,
you could
if we're
probably
talking,
use it in some way.
I'm sure there's a way, or I mean, even if you just make a copy of yourself, yeah, or a near
Right. Well,
copy of
this
yourself.
comes back to the thought experiment of, if you were to create a true transportation machine where, let's say, I'm in LA right now, I go into this transport machine, and then it basically scans all of my atoms, all of the structures in my body, and
Hmm.
then disintegrates myself, and then basically reconstructs it in, let's say, London.
Hmm.
Then, and let's say I do that every morning as part of my commute for work, and then one day the machine malfunctions and it does the copying and it does the replication, but it fails to disintegrate me. Then they're
Yeah.
like, "Oh yeah, sorry, there's been some sort of a mix-up. It worked fine, like you're in London, but now we're gonna have to kill you because the disintegration didn't work." I would be like, "No, like I'm the real me. Like don't kill me. That guy's an imposter." And so, like, that's a good reason why we wouldn't want to actually teleport ourselves somewhere.
Hmm.
But if we could at faster than light speed just see through the eyes of a camera elsewhere, or like go into an avatar that maybe has like the exact same physical structure as our own bodies, that's just like, sitting in London waiting, and then I can
Mhm.
just take over that body through quantum entanglement. Like that would be awesome. I don't know if it's possible, but like when I'm thinking like what would be like the most awesome application, like that's definitely up there.
Yeah, and who knows what happens if humans survive 1,000 years, what does that world look like? And I
Right.
think I think quantum computing is fundamental to that world. And I think, there's probably a bunch of different ways that quantum computing is going to evolve because right now, where I see the current state of quantum computing is we're in a similar state as when people were with classical computers programming with punch
Yeah.
cards.
Yeah, I wanted to talk about that too. So, to give a sense of how long this will take, in 1946, the first big computer was built by the US government costing $6.8 million dollars, and it was the size of a room, big
Hmm.
room. By the year 2018, which is, just around today's time, IBM can create a similar computer, like a microprocessor, that's the size of a grain of salt for 10 cents. Okay, so we went from $6.8 million dollars to 10 cents in 72 years, and similar computation power. So if we
Yeah.
think about like where we are now with quantum computers and where we may be 72 years from now, it seems quite likely that by the time, let's say, we're in our golden years, then the young kids, our grandkids, will be running around with like maybe with quantum computers in their pockets and just able to basically like manifest the world in whatever way they desire on command. And this kind of gets into the future scenarios, so maybe we should move to that if you're ready, or do you have something else to say?
Yeah, I mean, I would basically only say that the a classical computer is necessary like in conjunction with
Yeah,
a
yeah,
quantum
totally.
computer.
More of a
Um,
hybrid computer. Or,
yeah,
or even
but
you may not need your own quantum computer. You may just tap into like a quantum cloud computer that
yeah,
just
and that's pretty much what's happening right now, and
like
I'll
IBM
talk about
already
that at
has
the
one.
very end.
Yeah.
Yeah. But yeah, let's get into the scenarios. What do you think about the best case scenario then?
Best case scenario.
My best case scenario is one in which we are able to effectuate the simulation hypothesis that Elon Musk believes we're in already,
Hmm.
to basically play God to create worlds on command. So I was reading this book called The Simulation by this MIT computer scientist who also has built VR systems and is just a really all around smart computer scientist. And when you think about like what would be required to actually create a simulation in the real world, you could do it through 3D printing on the atomic and subatomic level. So if you could imagine you're like walking through a grassy field, like similar to how you would be if you're playing World of Warcraft, and it's like if you turn left, the pixels render in that part of the world when you walk in that
Mm.
direction. If you go forward, the pixels sort of render in that direction. And you could do it through light projection, which is another nascent field that I think we should at some point do a whole episode on. But you could
Hmm.
imagine, like, with sort of hologram light technology, you could make structures appear in physical space that aren't physically there if you touch them. So that would be sort of like an earlier way to basically have the same effect of augmented reality, virtual reality, without needing to wear glasses at all. Like you could just walk outside and you could have light projection create an ad for Coca-Cola outside your house and follow you around everywhere you go until you buy that sugary drink. Right? I'm not saying I would want that, but I'm just saying that's a possibility technically.
Okay.
And beyond that, if you wanted to create actual physical objects that aren't just light projections, you could do that through a quantum computation that 3D prints subatomic particles and atomic particles. And when you think about like what a 3D structure is, most of it's empty space. It's really just the structure, and you don't even really need the middle of the structure. You really just need the edges of it for it to feel solid and to have the full experience of this being a real physical object, even if it's like basically hollow on the inside. So you could imagine a world in the far future facilitated with quantum computing where you could basically just like walk around and reality is rendered on command however you desire, and you could basically just play God and will things into existence through a brain machine interface combined with quantum computing, combined with 3D printing on the molecular level, combined with light projection. And that's my best case scenario for the long future. When I think about the short term, I would just say that we have enough progress in quantum computing to keep Moore's law going. So that's what I would say, like, if we just keep progress so that the economy keeps growing, funding keeps going, then that would be like a great short-term outcome, because a lot of this is still very, very early. And then my medium term would be we're able to create better batteries. That's something we haven't discussed yet, but this is a major limitation in energy, is that our batteries suck right now. And even though we've got pretty good solar panels, we just can't store the energy well. And this is something quantum computing could solve, in addition to the other things we've talked about, like medical advances, business optimization problems, encryption. But I get most excited when I think about like the far future, like rendering reality on command. I mean, it's just so awesome, like thinking about what's possible, and then exploring other worlds remotely, and I would say also just fundamentally understanding the workings of the universe and having a grand theory of everything, whether it is a simulation or a many worlds theory. And we should also talk about that at some point, but I'll end my best case scenario there. I could go on.
So I similarly find it really interesting to think about the far future with quantum computing. And for my best case scenario, so I think, like I said earlier, quantum computing is a prerequisite for artificial general intelligence, or specifically sentient AGI.
Right, consciousness.
And, And one of the other things that I've been thinking about recently is it's a little naive to think humans are the final stage of evolution.
Oh yeah.
I think there's, especially if you think of 1,000, 10,000, a million years down the road, humans are either going to be extinct or humans are going to be completely different from what we think of as a human today. And I think one of the ways that we can keep the pace of evolution going is through an artificial general intelligence. And this is one of the things that I think Joe Rogan talks about a lot, is we're just eventually going to, like, we're just giving birth. We're almost like caterpillars making a cocoon that's giving birth to something else. And if that something else is AGI, this AGI has the potential, I think, to really understand what theories of everything, what a theory of everything would actually look like. And it could.
Do you think that could be possible through a brain machine interface, like an augmented human, or do you think it would require like a fundamentally different brain structure?
I think when I say, so let's pick this up from the point we can create a sentient AGI.
Yeah.
I think at first it will be useful to have both. I think beyond a certain point, the AGI will innovate so quickly that the limitations of biology, the limitations of biology are just too great, because it's not going to. I don't think that we're really going to explore the cosmos as biological creatures. There are way too many things that we can't handle as biological creatures because we're so tied to Earth. Right. Everything about our design is specific to Earth because we evolved here. And I think once we have something else that is different, and maybe it's pure, like maybe most of AGI is just pure information or light being sent from one place to the other. That I think once we reach that point, we can truly explore the cosmos. And I say we as in like whatever that thing is in the
Right.
future.
Life,
Um,
earthlings,
yeah. um,
whether they be
and
meat made or silicon made.
Yeah, or something totally new entirely. Like
Yeah.
we just have no idea. But I do think that we, in the best case, do just give rise to something that maybe doesn't have these negative impulses that a lot of humans have. Maybe it can truly be some sort of benevolent thing that
Well,
wants to explore, that just wants to understand the true nature of reality. And what
I
if
would argue that in if there were no evil, there would also be no benevolence. So if there's a world where every being is just a benevolent AGI, then benevolence itself is meaningless because there's no counterexample to that.
And maybe benevolent isn't the right word. Maybe it's stoic and purely scientific, and it's really
Uh-huh.
just trying to understand the nature of reality. And it could turn out that, the same way
With a
that
playground of
life,
humans to observe and enjoy and
or
hopefully.
the whole universe to observe and enjoy. Because
Yeah.
if you think of the first molecule on Earth, this first single-celled organism on Earth, that I mean, that period of like really small cells and single cellular or unicellular organisms on Earth was an extremely long amount of time. I think in like close to 1 billion years. These things were just kind of floating around in the ocean, but eventually things just kind of gain traction. And
Hmm.
I think there might be a similar thing in the far future where like AGI, this one AGI that was developed on Earth, is the universal equivalent to Earth's first unicellular organisms, and then we can
Hmm.
start to colonize the entire universe, or first the entire galaxy, and then the whole universe. And this can
Right.
expand
Well, what do you
further
think
and
about?
further.
I've also heard the argument that, in relation to the Fermi paradox, that perhaps the reason that we don't see other extraterrestrial civilizations emitting lots of energy from their home planets is because they realize that it makes a lot more sense to go inward rather than to explore outwards, meaning to create virtual worlds and simulations on like more of like a quantum level rather than like traveling light years across space-time to physical planets. What do you think about that sort of trade-off?
Um, I think I don't really know what the answer would be. I
Yeah.
don't know. The Fermi paradox is, there's a lot of different explanations for why we haven't seen something. It could just be that it's really hard to make life, and we just can't observe life because stuff is, even if there is life, it's so far away, like like several million
But I'm just saying,
galaxies
like,
away.
if humanity continues to progress, won't it make more sense to just create whatever virtual worlds we want rather than to explore externally? Or I guess maybe we'll at least we'll want to do both for as long as we're like physical beings because we love physical world stuff.
Yeah, I think that we don't understand enough about how the universe works and what a super intelligent species would actually do
Right.
and would be capable of.
Because
Because it's
I
possible that they could somehow manage to like enter the fourth dimension, and
right.
we physically can't perceive something that is in a higher dimension.
Well, I
And
could
that could
imagine
be,
like it does seem like you could through experiments understand fundamental insights about not just what's happening in this little quantum area, but the entire like quantum dimension. Because if you think about quantum field theory, which I find fascinating, it's basically that there are these different fields of activity, And if you vibrate on a certain frequency, it'll affect a certain type of structure, like electrons, which all happen to have the same sort of mass, energy, and behavior. Whereas if you vibrate on another frequency, you affect the whole nucleus. And another one is the whole atom. And another frequency is the whole molecule. And it's kind of like there are these fields. And so I wonder if it is even that meaningful to travel to other points on the space-time continuum rather than to just like study the different fields. And by studying those fields, maybe you
Yeah,
can understand principles about the whole field.
that's
And
possible. I mean, definitely possible. So,
right.
I'm I'm not sure what it would look like, but the explorer in me,
Oh
in
yeah,
the best
yeah,
case would just love to see, the whole universe colonized.
totally.
Um,
Yeah.
but anyways, yeah, maybe we move on to the worst case.
Okay.
What do you think?
Worst case scenario.
My worst case scenario, I'll start in chronological order. In the short term, it's that we cannot achieve a low enough error rate for quantum computers to be useful. So, in the short term, the worst thing is they just don't work enough for it to be worthwhile. In the medium term, my worst case is that whoever has ownership of the first truly effective and superior quantum computer will use that superiority to winner take all ends. Basically, you could game the stock market, or you could create medical advances for yourselves and maybe charge a ton of money so only the people at the top would be able to benefit. Like, there are lots of ways where if it's not democratized, like it could be an advantage for the small portion of people who invented it or who have ownership, and not to those who don't. I mean, you could also imagine if, like, for instance, China had the breakthrough first major quantum computer and they used that to like consolidate their power and
Hmm.
it affect their sort of worldview. So that's like sort of medium term, which is really not like that scary, but something to think
Yeah.
about. But the long term is where it actually gets pretty terrifying. And that's where we engineer something like, let's say, a misaligned general AI, or let's say some sort of nuclear catastrophe, or a virus, or just something that we maybe we couldn't even imagine. I mean, the way I think about it is Nick Bostrom's pulling a black ball out of the urn of invention,
Hmm.
right? Like, it's possible that because we're operating in the fundamental operating system for the cosmos, we could have some pretty terrible consequences if we're not careful. I don't know that for sure, but it does seem like, to Nick Bostrom's point, if there do exist some inventions that can spell our doom, and that seems quite possible given that, nuclear bombs are a thing and mass viruses are a thing, and then it's possible that we will discover something that cannot be undiscovered and that it could spell our doom. So it's fairly broad, my worst case, but
Yeah.
it really just points to the fact that we need to be very careful in this way, and that we should make sure
Hmm.
that whatever areas of quantum computing are developed, that they're always looking out for the whole rather than, trying to favor specific subgroups. Um,
Yeah. Yeah, I would say that mine are similar. The short, kind of like she said, the short term is we just don't figure it out. We don't figure out quantum computing. We can't we just can't do it because it's either too hard, there's not enough people in it, or there are some like laws of physics that make it nearly impossible without being in like a near vacuum everywhere. Because obviously we can't walk around with like absolute zero phones or absolute zero or vacuum sealed phones with
right.
a quantum processor. So there's a lot of limitations, and I think that might even be a longer term thing. Like it
That's what
it
I was
might be
thinking.
really
Maybe
hard to
we
do.
have like like a huge quantum computer on the moon or something, so that it's a lot easier to be near zero.
Yeah, yeah, that's possible. But then there's a lot of interference from the sun's particles because we get a
Oh,
lot of
right,
protection.
right.
We get a lot of protection from that stuff because of our magnetosphere. So
Hmm.
there's a lot of stuff out in space that we just can't see, but there's still interference out there. Um, but anyways, yeah, for The other thing, if we do figure it out, maybe for power consolidation, um, I mean, I don't think it's very likely because I think, unlike what most people think of as AGI and how the exponential increase in technology will, you know, make something so smart that it just becomes runaway and dominates the world, I don't think that's the case with quantum computing. I think the progress will be incremental enough. And I
Hmm.
also think that it'll be slower than classical computing because it is a fundamentally harder problem to solve. I think that it's probably not, maybe that's getting into the likely scenarios, but I don't think it's very likely that we have um, a computer that is, so advanced beyond all the other countries that it
Right.
creates
It is a
this
little,
power.
that's what I was thinking too. It's a little premature to worry that much about the worst case for this topic
Hmm.
because it's so early. So we're
Hmm.
probably better off worrying about climate change or,
Yeah,
benevolent AI in general as opposed to quantum AI. And yeah,
yeah.
so I'm with you. But
One
yeah.
one last thing to touch out to really get into a worst case is if we can create simulations with
Ah,
that,
yeah.
if we can create simulations, and we might be in a quantum simulation right now, and there might be, you know, billions, trillions, like unfathomable numbers of simulations going on right now by
Hmm.
some being. Um, if that is actually taking place, and if we can do that in the future, there are probably some of those simulations that are complete hell for everything alive in that
Right.
simulation. So that would be the worst case. It's just like this unimaginable hell, just something we don't even know. Like we just view it as, or whoever is simulating just views it as, okay, this is an interesting outcome,
Right.
in the name of science, without really thinking about the consequences of the suffering of what's going on. But I think that sort of simulation is so far in the future.
It's like
Like it
worrying
would,
about overpopulation on Mars.
I would say like it's worrying about overpopulation of the next galaxy. Like
Huh.
I think it's that far out that we can create those sorts of simulations. Um, but yeah, I do think it's something to at least put out there as a worst case.
Yeah.
So what do you think for the likely scenario then?
Most likely scenario.
My most likely scenario is that there will be useful quantum computers in our lifetime, but they will be in the cloud. They won't be a personal quantum computer, and they will still be for relatively niche purposes. So IBM already has a quantum computer that you can go on their website and you can run an experiment and just use a real quantum computer. So they're already available today. They're just very limited in, as far as like what they can compute and how complex the
Hmm.
queries can be. But that's going to get better and better. So I think that by the time where, that we have kids and where, our kids are sort of growing up and entering the job market, at that point, I think it will have meaningful contributions in biology, healthcare, space exploration, encryption, battery storage, business optimization. And I don't think we're going to achieve any of the worst case scenarios in our lifetime. But I think
Hmm.
that our kids are going to be tasked with making sure that some of the worst case scenarios don't become realized.
Hmm. Yeah, I would say something pretty similar. I do think that it's going to take a lot longer than some people would like or than they would think
Hmm.
to be able to run useful quantum algorithms. But there is going to be steady development, I think. And one of the issues right now is that we're essentially writing assembly code, which is a super low level language, meaning you have to specify a whole
Right.
bunch of different things to try to write this quantum algorithm. Like you have to define the exact quantum gates all along, the process. If we still had to do that with quantum or with classical computers,
Oh, it would take
we wouldn't,
forever. Yeah.
yeah, like there's absolutely no way we would have laptops on, in a home.
Right.
But I do think I mean, I know there is development to try to create high level quantum programming languages, and I think we'll probably see the programming languages develop a little bit faster than the hardware itself, because the
Hmm.
hardware is truly difficult to figure out. And like you said, it's also going to likely remain like this client server, like
Right.
it's going to all be in the cloud, meaning you're using your laptop, but you can define a quantum program and then just send it off to a quantum computer and then get results back.
Hmm.
And that's one of the things too that I think any listener, especially if you're a little bit younger, maybe you're in college or thinking about what to do with your life, or you just want to like redesign a career, you really don't need to understand quantum physics to write quantum programs. Yes, if you want to, write or create quantum computers in the actual hardware, yes, you need to know quantum physics. But if you have a really good understanding of like linear algebra and how matrix operations work, and some higher level concepts, I think anyone has the capacity to write a quantum algorithm. And like you said, the IBM quantum experience, that's what they call it. They
Hmm.
have a whole bunch of tutorials, like they'll take you
Yeah.
through how to actually write a quantum program and
There are
kind of
really
get.
good resources out there.
Yeah, and anyone can do it. I think this is one of those things where if you know how to write quantum algorithms, you're going to be so valuable at some point
Yeah.
in the future. It's just a matter of when. And if you just kind of
And I would
low
say
key,
also it's less about how good you were at science in school or math in school, and it's more about if you have a real interest and curiosity in this area. I
uh,
think that's an even bigger determinant of success because even if you're not the one writing the quantum algorithms, like for that you do need a good understanding of math and science, but even if you're someone who just helps further the field and public understanding, and I mean this
yeah,
whole area is going to become so much more important as time goes on that I think the biggest factor is whether you have interest and curiosity in this area and you're willing to really, delve in deep.
yeah, yeah. I mean, I couldn't have said it better. All of these, there's so many different angles that you can attack quantum computing from, and I think if we can really get a handle on it, the whole world is going to change.
Totally.
So the same way that classical computers revolutionized our world, I think we can experience a similar revolution, if not in our lifetime, the next generation beyond us.
Yeah. Yeah, and I think a good place to end it would be what is still unknown. Because one of my biggest gripes with how science is typically taught is it's taught as if most stuff has been figured out. But when we think about this topic in particular, so much has not been figured out and it has so many implications for everything else. Like, I
Mm.
just want to end on free will, consciousness, and the many worlds theory. All three
Or
of
the theory
these,
of everything.
or the theory of everything, but all of these areas are very much unknowns. They're big question marks. We don't know if there is just one reality that the wave function collapses and this is the one we're in, or
Mm.
it may be that there are many realities forking out, like Jean-Louis Bourget's Garden of Forking Paths. As far as free will, it may be that we're like avatars in a video game, choosing our own reality, flipping quarks, and literally creating the reality that we find ourselves living in. Or it may be that there is no free will. And with consciousness, we don't know how consciousness works, what organizational structure of neurons or some other silicon type would be
Yeah.
required to create a real conscious experience. We don't know how to create that in an AI. We don't know how it works in our own minds. So all of these are areas that are still very nascent, haven't been discovered, and anyone who's listening to this has the real possibility of making some big
We are all gathered
impacts
here
in this
today to
field.
talk about three
Yeah, I
very
think that's a
important
great place to
things.
end it.
All right, thank you everyone
We're
for
going to talk
listening.
about
This
what
been
has
the
happened,
Show, Quantum
what is
Computing,
currently happening,
and we hope
and
to see
what
you
will
next time.
inevitably happen.
The past, the present, and the future.
Our computer is picking up a strange signal.
The past, the present, and the future.
Hey futurists, if you've made it this far, you might be wondering who created the Hence the Future theme song. It was created by the Walden Brothers, and you can find them on Spotify. The Walden Brothers also produced the sound bites for the worst case, the best case, and the most likely future scenarios. At Hence the Future, we're always looking for ways to improve the quality of our episodes and our predictions. To that end, we're building a team of researchers to curate the most authoritative and highly vetted sources as the foundation for every episode. If you'd like to support these efforts, you can donate a small monthly amount at anchor.fm/hencethefuture. And if you haven't done so already, please rate and review the podcast on iTunes or wherever you listen to podcasts. We appreciate your support.